Number 1, FRQ Topic 4. They're all table problems on Topic 4. That's what groups them together. The height of a tree at time t is given by a twice differentiable function, where h is measured in meters, t is measured in years, and there's the table given to you. 2, 3, 5, 7, 10. There's really no reason for me to replicate this table, other than I want to, and it'll keep all my work in one spot. So years and meters. And let's see, so I could get average rate of change. I could integrate with the Riemann sum. So that's kind of what I'm thinking when I see a table, is the two main things are average rate of change in y over change in x, and I can approximate an integral with the Riemann sum. And usually they figure out some way to get me to do both of those things. Like, they don't come right out and say find average rate of change or find the Riemann sum. They ask something else that is supposed to lead me to one of those. That's usually how the tables work. So let's see. Use the data in the table to estimate h prime of 6. Estimate h prime of 6. Using the correct units, interpret the meaning of h prime of 6 in the context of the problem. So how do you propose I find h prime of 6? I've kind of already, that's the average rate of change. Well, h prime would be the instantaneous rate of change, but estimate means I'll use the average rate of change and say that's as good as I can get. And if I want it at time 6, then I should probably use the data points for 5 and 7. So 11 minus 6. And it asks about units, so I may as well include the units in my calculation, and then I'll have my units figured out as well. So 11 minus 6 is meters. 7 minus 5 is years. I suppose I could leave that as my answer. It would be correct. 5 over 2 meters per year. Okay, but then it says, using correct units, interpret the meaning of h prime of 6. So h prime of 6 is the, what is that? What does that tell me?
It's the rate of change of the diameter.
Rate of change of whatever h is, of height. Let's just say in year 6, during year 6, or at year 6.
At t equals 6.
Or at t equals 6. Interpret the meaning of h prime of 6. Okay, I think I did that. Part B. Explain why there must be at least one time t between 2 and 10 such that h prime equals 2. Oh. H prime of t equals 2 somewhere between 2 and 10. Any guesses on what we should do here? I don't really want to go through every single possible combination and see if I can hit 2.
MVT?
I think it's a
Value theorem?
I think it's an intermediate value theorem.
IVT.
An IVT. So I think 2 is going to be in the middle of extremes somewhere.
Yeah.
So let's see. Let's just try h prime at 2.5. Approximate, because I can't get an exact. So that's.
Oh yeah, I got the right thing. I just didn't get the right.
That's 0.5 over 1.
Which is 1.
So 1/2 meters per year. Okay, I think I'm just going to check the last one and see what that is. H prime at, I guess I could say 8 or 9 or 8.5. It doesn't really matter. I don't really know. It's an estimate. 3/4. Uh-oh. That doesn't help me. 0.75.
Try the middle.
So I need to find some spot.
No, you are.
I need to find some spot where I'm greater than 2, where the change is greater than 2.
Try something in the middle.
So, oh, maybe I should pay attention. I just did that. Usually there's little things like that hidden in the multiple or in the free response questions where, not always, but a lot of times what you just found is helpful. Not absolutely necessary, but helpful in the next one. So h prime of 6, we just found this, is 2.5 meters per year. So if h prime is continuous, then
It's twice differentiable.
then we're good.
Yeah.
Like, then there's some spot in between 2.5 and 6 where the slope is equal to 2. So if h prime of t is continuous, then I can make my claim that h prime of t equals 2 somewhere on, I don't know that I should say 2.5. I think I should say 2 to 7, because I don't know exactly where those slopes happen. Somewhere in there they do, but I don't know exactly where. Yeah, it might not be at 2.5. It might be at 2 or 3. So I'm going to expand my parameters to get from 2 to 7. Somewhere h prime is equal to 2. But now, how do I know that h prime is continuous?
It says it's twice differentiable.
Because
H is
h is twice
twice differentiable.
differentiable.
And differentiability.
Differentiability implies continuity. So that means h prime is differentiable. So h prime is continuous. You got to have all that in there, because if it wasn't continuous, then you could be hopping around and there's no guarantee that you went through the slope equals 2. But if it's continuous, I mean, I don't know, if a graph might help. So at 2, your slope was 0.5. And over here at 7, 8, 9, somewhere in there, or no, up to 7, it's 2.5.
Yeah.
It's like somewhere you got to go through 2.
Yeah.
That's intermediate value theorem. You don't have to label it as such. You can, but you don't have to. They changed that like 5 years ago, where you don't have to state intermediate value theorem. You just have to state, you have to use it and know what it is, but you could get by without saying it now because you've sort of explained it without using the name of it.
So you can't use MVT?
I don't think you could use MVT. Okay, I think MVT,
That's IROC equals AROC, right?
that is IROC equals AROC. If you had, but then you'd have to find somewhere where it equals 2.
That would be at 5 and H of 5, H of 3.
Yeah.
So from, yep, you could do it right there. That might be a better way to go.
I was worried.
Yeah, that would be a better way to go, because from 3 to 5, so that's a separate way to go, and I think you could do it either way.
Yeah. It's
Probably better to use MVT, because then you're definitely between 3 and 5. AROC is 6 minus 2 over 5 minus 3 is 2. And then by MVT,
that's differentiable.
A rock equals I rock. So that's 2 equals H prime of T
Somewhere from
somewhere on
3 to 5.
3 to 5. But MVT means I've got to say, to use MVT, I have to say H is continuous and differentiable. And I know that because
Y'all said so.
H is twice differentiable. Either way, they're getting you to say that differentiability implies continuity. They're trying to hit that. Either way you go, that's going to be that's almost certainly one of the points you would get in there. Probably the better answer. Part C, use a trapezoidal sum. Ugh.
Yeah.
With 4 subintervals indicated by the data to approximate the average height of the tree.
Can't we just we do have to use a trapezoidal sum.
So how do I find average value of a function, or average height?
1 over width times the integral.
Yep, so 1 over 10 minus 2.
But it says we have to use a trapezoidal sum.
Right, we're going to use a trapezoidal sum to estimate the integral.
Is that what that is?
Well, the trapezoidal sum can tell me, I can approximate that. Okay, if I just use the trapezoidal sum, my units are years times meters. That doesn't really do much. So they've got to ask average height to get it back to something sort of normal. But the trapezoidal sum will estimate the integral. So I still got the 1 over 8 out front, but then I've got to do the trapezoidal sum.
Which I forgot how to do.
Well, the area of a trapezoid is base times the average height.
Oh, yeah.
Base times the average height. So I'm looking at my table. The first base width is 1. And the average height would be 1.5 plus 2 over 2.
Do not touch anything.
Yeah, this is no calculator, so I am not going to mess with that.
No touchy zone.
It's a disaster waiting to happen. From 3 to 5, the width is 2. And the average height would be 2 plus 6 over 2. Again, try to avoid memorizing formulas. Like I can sketch a trapezoid and remember what the formula is. Okay, so that's 2 to 3, and it's certainly okay to label what you're doing. 3 to 5, 5 to 7 would be a width of 2, and an average height of 6 plus 11 over 2. And then from 7 to 10, the width is 3. And the average height is 11 plus 15 over 2.
If they want to know, they can.
And that's my answer. Yeah, I'm not messing with that. Presumably it's somewhere between 1.5 and 15, but I'm not going any further with that.
Not touchy.
Part D. The height of the tree in meters can also be modeled by the function g, 100x over 1 plus x, where x is the diameter of the base of the tree in meters. Okay, so that's not by time, that's diameter, height versus diameter. When the tree is 50 meters tall, the diameter of the base of the tree, I'll start translating this. So when g equals 50, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. But what is that? What did they just tell me? The diameter is increasing at a rate.
Like that.
So what is that in terms of variables? G is height, x is diameter. This is dx dt. This is how much it's increasing in diameter per year. So that's dx dt. I sense a chain rule type problem coming here. According to this model, what is the rate of change of the height of the tree with respect to time? So that's dg dt, not dg dx, because g is height and x is diameter. I want to know how it's changing with time. In meters per year, in the tree, when g equals 50. So find dg dt and then plug in g equals 50. Okay, so this is going to be a quotient rule problem. So f prime is 100, g prime is 1, so that, I guess that's not terrible as far as quotient rules go. So dg dt is, so gf prime, so 100 times 1 plus x minus fg prime minus 100x. Well, that was convenient what they just did there. All over g squared. But there's this chain rule thing, dx dt at the end.
Ugh. We found dx dt.
So we know dx dt gave us that. G is 50, we want dg dt, so I need x when g is 50. Well, I can do that. That's algebra. I don't know if this is going to be nice or not, but so g is 50, we're looking for x. 50 plus 50x equals 100x. So 50 equals 50x. Oh, well, they threw us a bone there by giving us an easy x to deal with. So dg dt when g equals 50, which is when x equals 1, is 100 times 1 plus 1 minus 100. Some of that will go away, but I'm not doing algebra. Like, I'm here to do calculus. 1 plus 1 squared times 0.03. And it didn't ask me for any interpretations or anything, or just so I'm done. Leave that alone. That was bad there at the end. That's yuck. You would hope that one's only worth 2 points and hope you got all the other ones. You know, even if it was worth 3 points and you got all the other ones, you'd be on track for a 4. So fight for every point you can get, but realize that getting most of all the questions will get you a 4. So looking at the time, I'm at 18 minutes, so that's a little bit long, but we did part B 2 different ways.
Yeah.